Om Amriteshwari Namaha Namashivaya. Another milestone for our Amrita group. We have our Astro Club, Amrita Astro Club today. And we have our guest, Professor Anand Narayanan with us. So we'll start the session. I warmly welcome all of you for this live session. It is going to be really interesting. All full of jam-packed with the students. And anxiously waiting for the new discoveries in the atmosphere. This is the most attractive subject. Okay, we'll start the session. So I request our Sriram to chant the prayer.
Sure.
Sure.
Om Dhyayamo Dhavalavagunthanapatim Tejomayim Naishtikim Snigdhapangavilokinim Bhagavatim Mandasmita Shrimukhim Valsalyamritavarshiniim Sumadhuram Sankirtanalapinim Shyamangim Madhusikta Suktam Amritanandatmikam Ishwari.
Thank you, Sriram. Now I request our guest, Anand Narayanan sir, to join the session. Sir, welcome.
Thank you. Thank you, ma'am.
Thank you. Yes, thank you.
Shall I start?
Yes, sir.
Yeah, so thank you, Srimati Jayanti Ganapati ma'am, for once again inviting me to interact with all of you. Thank you, Sriram, for that wonderful prayer. So I have been told that there are students from different classes who have joined. Most of you have a shared interest in astronomy. So let me quickly in 30 seconds tell a little bit about myself. So my name is Anand Narayanan. I teach and I do research in astrophysics at the Indian Institute of Space Science and Technology, which is a university under the Department of Space, Government of India. And this university is located in Thiruvananthapuram, from the main city about 20 kilometers towards the Western Ghats. And I've been there for the last 12 years. And we have students. It's a residential campus, which means all students who study under the university, they stay within the campus itself. And we have undergraduate, postgraduate, and PhD programs. So there are about 800 to 900 students who live on campus, and many of them are getting trained in the many areas of space science and space technology. Okay, so I would encourage all the students, especially those of you who are in high school, to go and look at IIST's webpage, Indian Institute of Space Science and Technology's website, because some of you would probably be interested in joining our institute if you are aspiring for a career in space science, space technology. Okay. So I'm going to keep the presentation part of this not very long, only for half an hour or less. Okay. So astronomy, as you know, is a very vast discipline. It encompasses everything that is there in outer space, right from planets and stars and star clusters and galaxies to the universe at large. Okay. And astrophysics is basically a way of looking at the world, the physical universe, through the prism of science, through the prism of physics. So whatever laws and theorems that you are learning in school right now, in physics, in science, those same laws and principles and theorems are used by astronomers to make sense of the universe that we live in. And in this field, we try to answer some of the most profound questions that the human species has ever asked. For example, did our universe have an origin? Does it have definite boundaries? How old is our universe? How matter was created? What is the nature of time? And last but not least, one of the most important questions that astronomy tries to answer is, are we the only sentient beings in this entire vast universe asking these profound questions? or could there be life elsewhere in the universe? So what I'm going to be talking about is about this last question of, are we alone in this universe or not? Beyond the confines of Earth, could there be life anywhere else in the universe? Now, one of the ways in which astronomers are trying to answer this question is by finding places beyond Earth where life can arise, where life can thrive, where life can exist. Okay, so life as we know it, the only example of life that we have is life here on Earth. That doesn't mean that there will not be life anywhere else in the universe. We do not know, and that is why it's important to search. So since life, the only example of life that we have is life here on Earth, we know that life here on Earth requires a very comfortable environment, like a planetary environment. So in the last 20 to 30 years, there's been a lot of research in astronomy to discover planets orbiting other stars. Okay, so planets orbiting stars other than the sun. These planets are collectively called extrasolar planets, or exoplanets for short. So today I'm going to be talking about this brilliant, this very exciting story of how astronomers have discovered planets orbiting other stars. What observational techniques do they use, and what do we know currently about worlds beyond the solar system? Okay, so that's what I'm going to be talking about. So let me start by sharing the slides. So Sriram can maybe tell whether you are able to see the screen.
Yes, ma'am. Yes, sir. Yes.
Yeah, thank you. So extrasolar planets and the search for habitable worlds. That is the title of the presentation. See, if you look at the night sky, and if you keep on staring at the night sky, you can see that the sky is filled with innumerable number of stars. There are untold number of stars in the night sky. So what you are seeing here is a picture of the night sky taken with a digital camera, multiple images stacked together. That's why you see the entire sky sprinkled with stars. So observations like this remind us that our sun is only one star in a galaxy that we call as Milky Way, and Milky Way contains 200 billion stars in it. So that is 200 followed by 9 zeros. So it will be very unusual to expect that only sun would have planets around it. There's no reason to expect that sun is a very special star in our galaxy. It's just like any other star in our galaxy. So for a long time, astronomers have been speculating that there should be planets around other stars. So now the question is, how do we go about discovering them? Now, as it turns out, it's not very easy to find planets around other stars for a number of reasons. I'll list some of the reasons here. I'll mention some of the reasons. Okay, so what you're looking at here is a picture of the sun and the planets of the solar system drawn to scale. What that means is that the relative sizes of the sun and the planets are accurate. So you can see that a star like the sun is 100 times bigger than a small planet like the Earth, and it's even 10 times bigger than the biggest planet in the solar system, which is Jupiter. Okay. Yeah, so that means that planets are intrinsically very small when compared to their stars. A planet is like a grain when compared to the star. Now imagine the star planet system being at a large distance from us. All the stars that we see in the night sky, they are at distances of about 10 or 100 or thousands of light years from us. So a light year is the distance that light travels in 1 year. It's a huge distance. So the stars that we see in the night sky, they are at hundreds and thousands of light years from us, which means that at those large distances, a star itself is going to look like a small dot. So now a planet that is even smaller than a star will be smaller than a dot. So that means when you try to look at a star planet system in the night sky with the help of a telescope, the star itself will be a point, and the planet, as you can see in this animation, will be smaller than a point. Okay, and the star is ridiculously bright when compared to the planet. Okay, a star is usually 1,000,000 to 1,000,000,000 times brighter than a planet. So it's like, you are trying to see a firefly that is sitting next to a floodlight. So think about a huge stadium floodlight. There's a 1,000-watt floodlight light that is glowing. Suppose there is a small firefly or a small LED that is glowing right next to it. We will not see the LED or the firefly. The LED or the firefly will be lost in the glare of the 1,000-watt floodlight. It's the same thing that's happening with exoplanets. When we try to take pictures of the night sky, the stars become immediately visible as point sources of light. The planets, which are intrinsically very small and very faint when compared to the star, we will not see them. The planet will be lost in the glare of the star. Okay, so I'll take questions towards the end. I know that some people have raised hands, so I'll take all those questions towards the end. So directly seeing exoplanets is not very easy. Fortunately, there are some indirect ways for finding exoplanets. Now, these are called indirect methods because in these methods, which I'm going to describe right now, you don't see the planet. Okay, our observation is on the star, and by looking at the behavior of the star, we will be able to come to the conclusion that there is an unseen companion to that star. There is a planet around that star. So even though we don't directly see the planet that is around the star, by doing observations on the star itself and by tracking its behavior, we will be able to make an indirect inference about the existence of a planet around it. Okay, and the two most successful indirect methods are, one is called the radial velocity method, and the other is called the transit method. Now, you don't have to really worry about the names of these things. Okay, I'm just putting them down here. Okay, so radial velocity method and transit methods are the two most important or two most effective or two most successful methods that have yielded the detection of exoplanets, extrasolar planets, planets around other stars. Okay. So let me quickly tell you about what radial velocity method is and what transit method is. So generally, in school, we study that the planets are revolving around the sun, okay, or planets revolve around the star. But in reality, the planet and the star, they are both going around what is called the center of mass of the star-planet system. So it's, the center of mass is a very easy concept to understand. If you have ever sat on a seesaw, okay, one person will be sitting on one side and the other person will be sitting on the other end. And there will be a point where the seesaw is hinged, right? There will be a point where it is fixed. And that point roughly corresponds to the center of mass of this seesaw system. So that is what center of mass is. So in reality, whenever we think about a star-planet system, the planet is actually going around the center of mass of the star-planet system. And the star is also not stationary. The star is also going around the center of mass of the star-planet system. Now, in most cases, like our solar system, if you take as an example, the planets are so small compared to the sun that the center of mass is used of the solar system is inside the sun itself. So as you see in this animation, sun doesn't actually go around in an orbit, okay, because the center of mass is inside the sun itself. But now you think about a hypothetical star-planet system where the center of mass is outside the star, as shown in this animation that you are seeing on screen. So as the planet revolves around the center of mass, the star cannot remain stationary. It also has to move. Only thing is the star will be moving around in tiny circles and the planet will be going around in bigger circles. So the star is not stationary, it's going back and forth in its orbit. This orbital motion is not very large, so therefore it's called as wobble motion or wobbling. Wobble means oscillation. So like a pendulum, it's oscillating. It's going back and forth with respect to the center of mass. And it is this wobble motion that astronomers measure, which helps them to conclude that the star is exhibiting this wobble motion or wobbling or reflex motion because it is under the gravitational influence of a companion, unseen companion around it. And by measuring how big this wobbling is, and what is the time period of this wobbling, how long does it take for the star to fully wobble once, we can estimate what is the mass of the unseen companion, how far away the unseen companion is from the star. So when I say unseen companion, I'm talking about a planet here, a planet around that star. So all these properties of the exoplanet one can determine by looking at this wobble motion of the star. So how is this wobble motion measured? I'll just quickly explain it in a minute. So all of you probably have done this experiment in school where you shine white light through a glass prism, and on the other side you see this rainbow of colors. So these rainbow of colors that you see on the other side, that is what a physicist would call as the spectrum of white light. Okay, so white light is composed of colors of different colors, and when you allow it to pass through a material like a glass prism, the light gets split into its component colors. So this rainbow is called a spectrum of white light. Now what astronomers do is they also record spectra of stars. So telescopes will be looking at light, collecting light from a star, and the light that the telescope collects will be sent to an instrument called a spectrograph. The spectrograph works like a prism. It will spread the light coming from the star collected by the telescope into its component colors. And what you get is a spectrum of the star. And then what you do is you keep on looking at the spectrum. If the star is not stationary, if the star is wobbling, then as you see in this animation, in the spectrum, you will see some periodic shifts. Okay. So you can see some dark lines which are present in the rainbow of colors that you see below. And what you are seeing over here is an animation of a star and a planet that is revolving around it. Okay, so this is just an animation. This is not real data, just to convey the concept of radial velocity method. So the star is wobbling, and because of this wobble, there will be a shift in the spectrum. Okay, sometimes the spectrum will shift towards blue, sometimes the spectrum will shift towards red. So there are these changes that you see in the spectrum, and these changes, if you constantly monitor, how big are the changes, what is the time period of these changes, those will give you an insight into what is the mass of the planet that is orbiting around the star, how far away the planet is around the star, how long does it take for the planet to go around the star, whether the planet is in a circular orbit or whether it is in an eccentric orbit, in an elliptical orbit. All these information you can gain from recording the spectrum of the star. So keep in mind that we have not actually seen the planet. Our observation is confined to the star, but through careful observations, we are able to deduce the existence of a planet around it. The other method is called transit method. So what I just now explained till now is the radial velocity method. Transit method also is an indirect method. Again, we don't see the planet. Okay, our observation is on the star. In radial velocity method, we were measuring the wobbling motion of the star, the wobble motion. In transit method, what astronomers do is they continuously monitor the brightnesses of stars. And when a planet happens to pass in front of the star, as you see in this computer animation, if a planet is passing in front of that star, then the planet will block a little bit of light coming from the star. So for a brief period, the brightness of the star will go down. The star will dim in its brightness. Now, once the planet completely moves out of the field, the brightness of the star will come back to its normal value. Again, when the planet comes back and comes in front of the star, again the brightness will go down. So the planet that is going around the star, every now and then it will keep coming in front of the star. And whenever it does so, you will see that the brightness is dimming down. And then it is coming back to its normal value. So this periodic dip in brightness can be used to infer the existence of the planet around that star. Now, again, let me remind you that what you are looking at here is a computer animation. In reality, we are only monitoring the brightnesses of stars in the sky that look like dots of light. We don't see the planet. Just by looking at the brightness dip, we are inferring that there is a planet around it. Okay. So now what happens there when there are multiple planets? So suppose a star has a small planet and a big planet. So what happens then is the bigger planet will block a larger amount of light and the smaller planet will block only a smaller amount of light. So that means the dip in brightness is going to be large when the large planet is transiting in front of the star. The dip in brightness is going to be small when the small planet is transiting in front of the star. So transiting, that word means coming in front, okay, moving in front of us. So hence this method is called the transit method. So how deep the dip is going to tell you how big the planet is. So radial velocity method gave you access to the mass of the planet. A transit method tells you how big the planet is. What is its size? Is it a small planet like Earth or is it a large planet like Jupiter? Okay, so now these are two indirect methods. In the last 20 years or so, because of some great advancements in optics and optical engineering, so the way light is recorded, the way light is manipulated, the way light is measured, that is what is called the field of optics. Okay, so because of the developments in the field of optics, it has now become possible to take direct photographs, direct pictures of planets that are orbiting around other stars. It's not very easy, but it's not impossible either. Okay, so astronomers now have the technology to do that. So what you are looking at here is as actual telescope photographs of exoplanets. In the center, what you see is it looks like a donut kind of thing. That is where the star is present. Now, what astronomers have done is they have taken a picture and they have removed the light from the star. They have taken the light from the star out. They have subtracted the light out. And therefore, this part of the region where I'm pointing with my mouse pointer, that region is looking a little bit funny because you have taken the light from the star out there, and there are some residual fluxes still present. Okay, residual light that is still present. Okay. So what you're looking at here, as I was trying to tell, I've started sharing my slides again. Hope it's visible. Sriram, all good?
Yes, sir.
Yeah, thanks. So what you're looking at here is the light from the star has been taken out from the center. So that's why it's looking like some donut kind of thing. But around it, you can see 4 objects which have been marked B, C, D, E. So these 4 objects are planets that are revolving around the star. The star's name is HR 8799. You don't really have to remember it. Astronomers refer to stars in the night sky by using some catalog number. So it's like, your vehicle has a vehicle registration number, right? Or you have a unique ID or an Aadhaar card, something like that. Similarly, every star has a catalog number. So HR 8799 is the name of that star in that catalog. And B, C, D, E are 4 planets that are revolving around that star. Now, how do we know that these are the planets that are revolving around the star? That's because astronomers have been constantly monitoring the system for over a decade now. And what you are going to see now is the same star, HR 8799, and the 4 planets around them. Only thing is, this is a GIF animation that has been created by putting images together for a period of roughly 7 years. Okay. So at the bottom, what you see is 31st of July 2009, and that number will keep changing. The 2009 will proceed all the way up to 2016. That means it's 7 years of data. In the center, the black patch is the star HR 8799. The light from the star is blocked out. You can see 4 bright dots around it. Those are the 4 exoplanets around that star, BCDE. The animation is very short. Let me just play it. So this is real data. This is not a computer generated image or anything. This is real data, and you are seeing the planets revolving around the star. So these are actual images of exoplanets. Okay, I'll show you one more example. Beta Pictoris is the name of a star, and that star's light has been taken out from this image. That is why you see a black circle here, because the light from the star has been subtracted out. And what the small bright object that you see to the right of it, which I'm pointing with my mouse pointer, that's a planet orbiting the star Beta Pictoris. And watch what happens with the passage of time. So as time progresses, you see the planet moving with respect to the star. So if there are alien astronomers, if there are astronomers who are living in some other planetary environment, and if they do similar observations of our solar system, they are going to see some of the large planets of our solar system, like Jupiter, Saturn, Uranus, and Neptune, going around the sun in very much the same manner in which we are seeing these planets going around these stars. Okay, so now 1995 is when the first planet outside of the solar system was discovered around a star like the sun. 1995. So about 30 years have gone by, and in this 25 to 30-year time period, astronomers have found more than 5,000 planets orbiting various stars in our own Milky Way galaxy. And that number is increasing as we are speaking. Okay, every week, every month, new discoveries are happening. New exoplanets are being found. Of this 5,000 plus exoplanets that we currently know of, most of the planets are like Jupiter and Neptune. Okay, but 30% are like Jupiter and Neptune, and a smaller number are planets of the size of Earth. So that's what is marked here as terrestrial planets, small rocky planets like Mars, Venus, and Earth. The reason why the number of rocky planets or terrestrial planets or Earth-like planets, the reason why those planets are smaller in number is because it's very difficult to find them. Doesn't mean that they are not there in the universe. Probably every planetary system has rocky planets also present in it, like it has gas giants. Only thing is, it's easy to find big planets around stars, and it's very difficult to find small planets around stars. Okay, so there is a selection effect. There is a bias there in our observations. So now the question is, now that we know that planets are very, very common, almost every star has one or more planets revolving around them, then the question is, are any of these planets Earth-like? So when we say Earth-like, what we mean is, do any of these planets have atmospheres? Do any of these planets have the prerequisites for life? Okay, so we know that life on Earth is heavily dependent on its atmosphere. It's also heavily dependent on certain molecules like water. Okay, the first life forms on Earth originated in the ocean. Even now, all life on Earth, nearly all life on Earth depends on liquid water. And the presence of liquid water is a kind of prerequisite for life on Earth. So if you are thinking about life similar to Earth on other planetary environments, then we can define this question, or we can try to answer this question by asking, do any of these other exoplanets, do any of them have conditions that are favorable for the existence of life, conditions that are conducive for life? So what I'm going to be talking about in the next 5 minutes, and I'll stop my presentation after that, is what is currently happening in this field of research of exoplanet studies. Before 1995, the only planetary system that astronomers knew of was our own solar system. In the last 25 years, astronomers have perfected the techniques for finding planets around other stars. Now, now the discovery of extrasolar planets has now become a routine thing. Okay, it's very easy to discover exoplanets now because we know how to do it. So now what astronomers are trying to do is they are trying to see whether they can assess the presence of life on these exoplanets, whether they can find whether life is present on these exoplanets or not. Now, as you can very well imagine, these planets are revolving around stars that are hundreds or thousands of light years from us. So it's impossible to send a spacecraft to any of these planets and go to those planets and take a picture and send it back, because even a spacecraft with the current propulsion technology will take 100,000 to millions of years to reach some of these planets. So we don't have that much time to wait. So what astronomers are trying to do is they are trying to see whether with existing data, whether with the data that we can collect with telescopes, can we infer whether these planets are supporting life or not. And the way to understand this is, astronomers are trying to find whether these planets have an atmosphere around them. And if they have an atmosphere, what is the chemical composition of that atmosphere? Okay, what kind of molecules are present in the planet's atmosphere if it has an atmosphere? Now, why is this important? It is important because if there is life on a planet, that life can alter, can change the chemical composition of that planet's atmosphere. And how do we know that this is happening? Well, you look at our own solar system. If you look at our own solar system and take the three inner planets, Venus, Earth, and Mars. So here what you are seeing are actual images of the surface of Venus and the atmosphere of Venus. The surface of Earth, 70% of Earth's surface is covered by liquid water. So this is a representation of Earth's surface, and that's Earth's atmosphere. This is Martian terrain on Mars, and this is Martian atmosphere. So if you now look at these three planets, Venus is a bit closer to the sun and that compared to Earth, and Mars is a little bit farther away from the sun compared to Earth. But they are roughly at the same distance from the sun. It's not like they are very far away from each other. So even though these three planets are roughly at equal distance from the sun, when we look at the three planets, we find that Earth is very different compared to Venus and Mars. Okay, if you look at the atmospheric composition of these three planets, Venus and Mars's atmosphere is dominated by carbon dioxide with trace amounts of molecular nitrogen. Okay. Venus has a very dense atmosphere. Mars has a very wispy thin atmosphere. But whatever atmosphere is present, the composition is primarily CO2. Whereas if you look at Earth, CO2 is only present in very small amounts in Earth's atmosphere. Most of the Earth's atmosphere, nitrogen is present, and about 20% of the Earth's atmosphere is made of molecular oxygen. That is 1 part in 5 is molecular oxygen. So now the question is why, how come that Venus and Mars have very similar atmosphere and Earth has a very different atmosphere? The answer is that when these three planets formed, okay, 4,500 million years ago, when these three planets formed, they had very similar atmospheres. Now, roughly 2.5 billion years into the past, the first life forms on Earth originated. So these life forms were cyanobacteria, microbial life forms, cyanobacteria, blue-green algae, things like that, phytoplankton, marine life forms, marine microorganisms. And these early life forms, they processed food or they processed energy through a process called anaerobic metabolism, which means they took in carbon dioxide from the atmosphere, converted it into energy, and then as a byproduct of this metabolism process, they released oxygen into the atmosphere. So with the emergence of life 2.5 billion years ago, the oxygen levels in the Earth gradually started increasing and CO2 levels started coming down. Now, even now, the abundance of oxygen in the Earth's atmosphere at the 20% level is maintained by marine life forms and the plants and the shrubs and the trees that we see on land. If all life on Earth were to vanish today, then in the next 100,000 years, all the oxygen in the Earth's atmosphere will either react with minerals on the surface or they will dissolve in Earth's ocean. So the presence of oxygen, ozone, water vapor, and some other molecules like methane in the Earth's atmosphere is an indirect indication that Earth has biomass, Earth has life. We don't see these molecules in the atmospheres of Mars or Venus because they are not supporting life. So these molecules, which are indicators of life on a planet, they are called biomarkers. Biomarkers. So what astronomers are now trying to do is they are, in addition to discovering exoplanets, they are also trying to see whether they can discover the atmospheres of these exoplanets and whether they can analyze the chemical composition, what molecules are present. So if they find that, if they discover a planet like the Earth, a rocky planet like the Earth, or orbiting around a star, if they find that the planet is holding on to an atmosphere, and if there is abundance of O3, that is ozone, or oxygen or water vapor, then that is an indirect indication that indicator that there is ample life present on that planet. So that is what research is doing right now. Okay, I'm skipping all these things. Then let me quickly wrap up by saying that this is a field in which rapid progress is happening. Okay, as I speak, advancements are happening in this field. And in the last 25 years, our understanding of planets have completely changed because of all these discoveries. See, prior to 1995, when I went to school, we were taught that the only planetary system that we know of is the solar system. So we have the sun and the planets that are revolving around the sun. We have the small rocky planets orbiting close to the sun, and we have the large gaseous planets orbiting further away. Now we know that our solar system is only one way of arranging planets around stars. Every star that we see in the night sky probably has one or more planets revolving around it. It's just a matter of discovering them. That means that probably there are more planets in our galaxy than there are stars. So there are 200 billion stars in our galaxy, Milky Way, which means there are probably more number of planets in our galaxy. So that increases the odds of at least somewhere in some part of the Milky Way galaxy, at least there could be planets that are similar to Earth with a dense atmosphere, with liquid water, and with conditions that are conducive for life to exist. And finally, I want to say that, as I mentioned, we have in the last 25 years, astronomers have discovered more than 5,000 planets orbiting around all various stars. So suppose this is our galaxy. Okay? So let's say that this is our Milky Way galaxy. This red dot is where we are located. The solar system is. The sun is not in the center. The sun is about 2/3 distance from the center of our galaxy, about 23,000 light years away. All the 5,000 plus planets that I just now showed you, they are discovered by looking at stars within the local environment of the sun. Most of the galaxy is yet to be searched. So in the coming years, there are going to be more and more planets that are going to be discovered. So this discovery of exoplanets has rekindled human interest in this question of, are we alone in this universe? Okay, so we do not know whether there is life elsewhere in the universe. We do not know whether outside of Earth, whether there is life within the solar system or beyond. But now we are taking small steps, small baby steps towards answering them. So the discovery of exoplanets, finding atmospheres of exoplanets, looking for biomarker molecules, those are all the steps in that direction. Okay, and finally, I just want to end the presentation with this very famous quote by the science fiction writer Arthur C. Clarke. To the question of whether we are alone in this universe, Arthur C. Clarke said there are two possibilities. Either there is a cosmic loneliness to our existence, or maybe we are not alone in this universe. Both are equally interesting possibilities. So maybe we will find an answer to this in the coming years. And maybe some of you who are listening to this lecture, you will go on to become astronomers who will be making those important discoveries. So with that, let me stop and I'll be happy to take questions.
Really, sir, it was a actually wonderful session. As you said, we were under the impression that only 9 planets revolving around and all those details were taught us. And we also used to teach that to children. But now the time has changed and you have kindled a question, are we alone? That's really a good thought, a good seed that will make the children, become passion in the space. So I think, thank you so much. You are providing so fresh information which are new to us. Thank you so much, sir. Now it's a time for Q&A. So you can come forward one by one. I think Sriram will coordinate now. I will keep away.
So the voice was okay. The voice was coming through.
Yes, the voice was correct.
Yeah,
I know
because in the beginning, somebody mentioned in the chat box that I was not audible.
But it was audible only. Maybe their technical problem, but it was the Aditya and welcome. Okay. Thank you, sir. Thank you.
Thank you. Thank you.
Sir.
Yeah, Sriram, go ahead.
Sir, may I ask a question?
Yeah, so I'm not able to see who it is. Is it Sriram or?
Yeah, yes, sir. It's Sriram.
Yeah, Sriram, go ahead. Yes.
Sir, what do you think there existed before the Big Bang?
Yeah, so that's a very tough question to answer. So, as many of you know, there are multiple lines of evidences that seem to indicate that our universe had an origin. So that which is what we very loosely refer to as the Big Bang. Now, the important thing to remember is that Big Bang was the origin of everything that we know about in this universe. That means all the matter that we know of, the dark matter, dark energy, everything, all the other things, including space and time. Space and time also had its beginning with the Big Bang. So now, if time itself had its beginning with the Big Bang, then how do we make sense of this question of what was there before the Big Bang? Okay, so there was no before.
So,
Right?
so how did the Big Bang happen if there was nothing before it?
Yeah, so that is a question to which science does not have an answer. So all our theories about science, all the physical laws, the physical constants, everything came into existence after the Big Bang. So with the tools of science, we can only probe to the moment that happened just after the Big Bang. From that point onwards, we can use the framework of physics to explain what could have happened. Now, our laws of physics break down at the moment of Big Bang or at the moment of creation, if you want to refer it like that. Okay, so with the language of science or within the framework of science, we cannot answer this question of how the Big Bang happened or what existed before the Big Bang. Okay, so this is what it is.
Okay, sir.
Great question, yeah. So there are lots of questions popping up on the chat. I think, Sriram, you're going to read those, right?
Yes, sir.
So somebody has, Adityan has asked, can you talk about the Big Bang?
Sir, Adira has sent in the chat. Do you think wormholes are possible?
Yeah. So the idea of wormholes probably you got by watching this movie called Interstellar. I'm sure many of you have watched it. It's a Christopher Nolan film. And so in that movie, they talk about connecting 2 points in space through a dimension that is beyond the 3 spatial dimensions. So that's what a wormhole is. Now, within the framework of physics, using the equations, using the mathematical equations of physics, you can come up with the idea of a wormhole. Okay, but there is no, to my knowledge, there is no observational evidence for the existence of wormholes. But that doesn't mean that they do not exist. Theoretically, it is possible for wormholes to exist. But observationally, nobody has yet found the existence of wormholes. So that's where the field is right now. So that's my short answer to your question. So since you have asked, do you think wormholes are possible? Yes, but we don't have a direct evidence of their existence. Theoretically, yes.
Okay, sir. Swati and Akash, they want to ask a question.
Sure.
Yes, sir. Sir,
Yeah.
can't you
Yes.
take plants from Earth to Mars and give them some water there and make them survive there with some water? And because there is a lot of carbon dioxide, just give them some water and they'll absorb the carbon dioxide, and then can't you make life on Mars also?
Yeah, excellent. Very good question. Yes. So this is called terraforming. Terraforming means you change the terrain of another environment by bringing in life into it. So people are talking about doing these kind of things. So as you said, you take a life form from here, a plant life form from here, and you take it to Mars. Only thing is, you need to provide a little bit more conditions than just liquid water. You need to give it some more pressure, air pressure, than what is currently there on Mars. Mars has a very thin atmosphere. So which means the atmospheric pressure on Mars is very, very small. So you probably need to house it in some kind of a greenhouse facility for some time till the plant grows, but it is possible. So let me tell you that there is a discipline, there is a branch of interdisciplinary field of research called astrobiology, where they are trying to look at where they are trying to look at the survival of life beyond the confines of Earth. So there are satellites that are orbiting around the Earth. There is the International Space Station, you may have heard of it, where astronauts are living. So in the International Space Station, astronauts are trying to grow plants. They are taking seeds from Earth and they are trying to see whether the seeds would germinate in the low gravity environment of the outside the Earth and at the International Space Station, and they are trying to see how to grow those plants. They are also taking small living creatures like fruit flies and other things, and bacteria they are taking with them. They are trying to see whether these small microorganisms can multiply themselves, can thrive in the kind of hostile environments that exist outside Earth. So there are many such biological experiments happening. And as you asked in the question, the ultimate goal is to actually go to Mars and start growing plant and other life forms there, terraforming Mars. Okay, so that will happen. It may not happen immediately because so far human beings have not set foot on Mars, but maybe in the next 100 years, in your own lifetime, you will probably be hearing about biological experiments like growing plants being done on Martian terrain. Okay, so very, very interesting question.
Sir Gautam has asked in the chat box, is there something faster than the light?
Is there something? I'm sorry, can you repeat this?
Is there something faster than light?
Yeah, so as far as the rules of physics tell, nothing with mass can travel with a speed greater than the speed of light in vacuum. So nothing can travel than light, and nothing with rest mass. So rest mass means if the object is not moving, if it is having a non-zero mass, that is called its rest mass. So any object with non-zero rest mass cannot travel with the speed, greater than the speed of light. Now, there are these hypothetical objects called tachyons, which people have talked about, which Professor E.C.G. Sudarshan had worked a lot on. So they are, I don't know whether tachyons have been detected or not, but I don't think so. So they are these hypothetical objects which can travel faster than light, but other than that, nothing can travel faster than light in vacuum.
They can introduce themselves and then ask question.
Yeah. That.
Oh, okay, sir. Next, Aditya Anup is here with a question. 1 minute.
Yes,
Aditya, you may.
The
Yes,
question
Aditya.
is, how do the planets keep on orbiting their stars without a stop or getting absorbed by the star?
Yeah, so the force that keeps them in orbit is the force of gravity. So there is a balance between the gravitational pull that a star exerts on a planet and what is known as the centrifugal force, which is like a push that tries to push the planet out from its orbit. So it's very much like, if you must be knowing this, if you tie a small rock onto a string and if you swirl it, okay, it will keep on orbiting. The moment you leave the string, the object is going to go in a certain tangential direction. So the reason why it's going in a tangential direction is because of the centrifugal force, which tries to push it away. And the gravity in this small example that I talked about with a string and a stone and you swirling it, the gravity is the string and the hand that is holding the string in place, the stone in place. So there is this unseen hand of gravity that is trying to keep the planets in its orbit through the force of attraction, which is what gravity is. And the centrifugal force is trying to make sure that the planet doesn't fall into the star because of this pull. So it's like a push-pull equilibrium. Now, because it's an equilibrium state, it's a balance of these forces. the planet that is in orbit remains in that orbit. Now, the orbit can decay if the planet were to lose some of its energy as it's orbiting. For that, friction is one possibility, but in space, there's nothing, right? So you need something to rub against for frictional forces to take energy away from you. Suppose you start rolling a ball on the ground, you will find that the ball will come to a stop after a while. That is because the air resistance and the friction with respect to the ground is taking away the initial energy that you injected into the ball by throwing it onto the surface or by rolling it along the surface. So there's friction, but in space there's no friction. So these planets continue to orbit around the sun forever, okay? Unless there is some other kind of perturbation that happens from outside. Yeah.
Thank you, sir. Next, Devasarang would like to ask you a question.
Yes, Devasarang.
Sir, how the planets, the telescopes find the atmosphere of a planet?
Yeah, that's a good question, Devasarang. I did not go into it because I did not have enough time. So the way this works is that let's say that this is a star and there is a planet that is moving in front of the star. If you look at what I'm doing through the webcam, you can see. So you are the observer and my hand is the star and this is a planet that is moving in front of the star. Now, when the planet moves in front, as I told you earlier, the planet will block the light from the star for the duration of time. Now, a little bit of the light will pass through the atmosphere of the planet. The surface of the planet will block the light. Devasarang, you can mute your microphone. Yeah. So the planet's surface will block the light, but the atmosphere of the planet will allow the light to pass through. So some of the light that is passing through the atmosphere, as it passes through the atmosphere, the molecules in the atmosphere will absorb some of the light. So which molecule is present will determine what kind of light gets absorbed. Whether blue light gets absorbed or orange light or red light or yellow light, which color light gets absorbed depends on what molecule is present on the planet's atmosphere. So what astronomers do is when the planet is transiting, they try to record a spectrum of that star. And in that spectrum, when the planet is transiting, they'll see that there are suddenly some absorption lines. There are suddenly some light that is missing. And that missing light is because the planet's atmosphere, the molecules in the planet's atmosphere have absorbed that light. So this is called transmission spectroscopy. And using this observational technique, they detect the atmosphere of the planet and the chemical composition of that atmosphere. Okay, that's what it is.
Okay, sir. Aravindas has asked in the chat box, even if there is life on the other exoplanets, can we travel there or can the creatures living there travel to us anyway?
Yeah, so with the current rocket propulsion technology, we will not be able to travel to any of these exoplanets. Now, the closest star to the sun is a triple star system called Alpha Centauri and Proxima Centauri. These stars are at a distance of 4 light years from us. And astronomers have discovered that those stars are planets around them. So what that means is if today you send a spacecraft at the speed of light, it will take the spacecraft 4 years to get to Alpha Centauri. Now, our spacecrafts cannot travel at the speed of light. They cannot travel at any speed close to the speed of light also. So with the current propulsion technology, it's going to take decades or even maybe centuries to reach there. So right now we cannot do it, but that doesn't mean that we will not be able to do it ever. Okay, as we find out better and more efficient ways to propel spacecraft through space, we may be able to do this in a slightly shorter time period, at least to the nearest stars, if not to all the stars with exoplanets. So once we go there, we will be able to take, I don't think the initial missions are going to be manned missions, human missions. They are going to be robotic missions, and they'll probably take pictures very close to those planets, and they'll send those pictures back to us in the form of electromagnetic waves, which we can receive here, and we can see those photographs. So those things will happen probably in the next 50 years or so. There are already talks within the scientific community of doing such things.
Okay, so next, Manasa has asked in the chat box, how many universes are there in the space?
Yeah, so as you know, the word uni means one. So universe means there's only one universe, but there is this idea of multiverses. Okay, so multiverses means multiple universes, okay, if you can think of it like that. There is no evidence for the existence of multiple verses, but people using some ideas that are rooted in quantum mechanics, people talk about the possibility of the existence of multiple universes. But so far, we have not observed anything. All that we have observed belongs to the universe that we live in.
Okay, so next, Durga is here with a question.
Yeah, go ahead.
Sorry, sir, my question was already answered.
No problem.
Okay.
Yeah, thanks.
Next,
Durga.
Veda, is she ready with a question?
Yes, Veda.
Good afternoon, sir. I have a doubt. Are UFOs still existing and are we connecting with them?
Okay, so UFO stands for unidentified flying object. So if you cannot identify an object that is flying through the sky, then technically that qualifies to be a UFO, because you're not able to identify, you're not able to recognize what it is. So unidentified flying objects. And so there have been many reports by citizens, by common people, that they are seeing like interesting objects flying in our sky, in Earth's sky. Okay, and since they are not able to identify what it is, they generally refer to it as UFOs. Now, none of these UFOs claims have been substantiated or have been proven to be too beyond measure. Just because you see something that is moving in space and you're not able to identify what it is, doesn't mean that those are aliens visiting us, if that is what you're asking. Okay, extraordinary claims require extraordinary evidences. That is one thing that you have to always remember in science. If you are going to come up with some extraordinary claim, then you need to back it up with extraordinary amounts of evidence. Now, many of these UFO sightings have happened in North America, in US. And these UFO sightings always have happened in a place called Sector 31, which is in a place called Nevada in the US. And Sector 31 is an area where US military is doing a lot of research and development. So the US Air Force is building next generation aircrafts, war aircrafts, okay, warcrafts. And sometimes they do these test flights of these stealth aircrafts. So people who are living in the kilometers away from these secret facilities, when they see these interesting objects that don't look like an aeroplane, but they are flying through the sky, they say that, okay, it's an UFO, it's an alien visiting, etc. But unfortunately, none of those claims are substantiated with proper evidence. So UFOs remain as a topic that is confined to science fiction. To the best of my knowledge, I don't think they correspond to actual extraterrestrial beings visiting us. Yeah, sorry that was a depressing answer, but yeah, that is the truth.
Okay, so next, in the chat box, Aditya Anup has asked, how many planets keep on orbiting the stars without a stop or getting absorbed by the star?
Yeah, so a lot. I mean, that number varies. There are stars with 2 or 3 planets that astronomers have discovered. There are stars with 7 to 8 planets, like our solar system, that have been observed. See, when our solar system formed 4,500 million years ago, probably there are more planets than the 7 or 8 that we know of right now were orbiting around the sun. But not all of them were in dynamically stable orbits. Not all of them were in stable orbits. Some of the planets, because of gravitational forces, either they got thrown out of the solar system or they... So what we now see in our solar system are those planets that happen to be in very stable orbits. So right now what we are seeing is a cleaned up solar system with all the stable planets going around the sun. Okay, so to answer that question, how many, that number is entirely arbitrary. It can be any number.
Okay, so next Malavika is here with a question.
So can we take the last 3 questions?
Okay, okay, sir.
Yeah.
Yes, sir.
It's
Malavika is
just
here
that
with a question.
I'm recovering from a throat infection, so I
Yes, sir.
cannot talk
Don't
for
pain
long.
yourself. Okay,
Yeah.
okay, okay.
Yeah.
Please, please.
So I will take 3 more questions.
Yes.
Sir, now I have heard that the sun is now slowly expanding and the moon is attracting towards the earth. So is it any sign of any danger, or is it dangerous?
Yeah. So the sun is slowly growing in size. That fact is true. Okay, so it will take me a lot of time to give you all the details of it, but let me just quickly explain to the best of my ability. See, the star like the sun is glowing. It is shining because of nuclear fusion reaction that is happening in the core of the sun. So every second, tons of hydrogen is getting converted into helium in the core of the sun. Now, there is only a finite amount of hydrogen that is present in the core of the sun. As the sun is burning, it's slowly exhausting this amount of hydrogen that it has in its core. It's like, you fill your petrol tank with petrol, and then you take your two-wheeler or your car for a drive. As you keep on driving, you're expending that energy, expending that fuel, and the fuel amount comes down. The same way the sun is shining, and so the hydrogen in the core is coming down. So since the hydrogen in the core is coming down, some changes are happening to the sun. One of the changes is that it's slowly growing in size. Its amount of light output is also increasing. But this is not very alarming. It's not happening at a very alarming rate right now. For the next 4,500 million years, sun is going to continue to shine like the way it is going to shine. It is shining right now for roughly the next 5,000 million years. 5,000 million years. So in terms of the lifetime of the sun, we have reached halfway through. Since the beginning of since the birth of the sun, we have reached halfway. Another 5,000 million years, the sun will continue to shine like this. After that, the kind of changes that I talked about, the sun growing in size, etc., that will become very dramatic. And at that point, life on Earth will be completely wiped out. The sun will become so large that Mercury and Venus will go inside the sun. It will be engulfed by the sun, and the surface of the sun will become as big as the orbit of the Earth around the sun. So you can imagine, when this happens, the atmosphere of Earth will be completely blown out. It will evaporate out, and the conditions will become so difficult for higher life forms like us to survive. Which is why it's very important that we start thinking about, if we are interested in preserving life forever, we should start thinking about becoming an interplanetary species. We should start thinking about how to move or how to go to other planets, how to leave the solar system, etc. And that is what all the space agencies, the Indian Space Agency through its Gaganyaan mission, the European Space Agency, the American Space Agency, they are all trying to look at the long-term survival of humans and other life forms in space. Okay, but we are at the very beginning of those kind of research, and you don't have to worry. There's still a very long time to go before before all those changes happen to the sun. Much before that, we will all be gone anyway. So, but human species would like to live beyond that. Yeah.
Thank you, sir. Next, Dia's here with a question.
Yes, Dia. Dia, are you there?
Okay. Next, Anusri. She's here with a question.
So Dia says she's unable to unmute herself.
We will connect to her. Let me try.
Yeah, sure.
Anushree, you may ask your question.
Sir,
Yes. Go ahead, ask your question, honestly.
sir, is there any closest exoplanet that can support life?
Is there any? Can you say that again? Can you repeat the question, please?
Is there any exoplanet that can support life?
Yeah, okay. So there are actually many recent discoveries have shown that some of the planets are terrestrial mass planets, which means they have masses and sizes comparable to that of Earth or Mars and Earth or Venus, and some of them have atmospheres also. Although the detection of biomarker molecules has not yet happened, like O3, oxygen, water vapor, etc., that has not yet happened. Telescopes like the James Webb Space Telescope is supposed to give us those kind of discoveries. So in the coming years, I'm sure there are going to be exoplanets that are discovered with atmospheric composition that is similar to that of Earth, which means that they are supporting life. Now, there are some exoplanets that seem to be favorably positioned with respect to their star for water to be present in its liquid form in those planets. But these are all based on indirect inferences, because as I already mentioned, we cannot really go to those exoplanets and verify it for sure. But based on indirect inferences, some planets do resemble that of Earth, etc. So there are some habitable planets, so to speak. Okay.
Okay, so we have come to the last question. I'm really sorry because many children have posted their questions in the chat box. So we due to time limit, I'm not able to ask that question to sir. Please post your messages in the WhatsApp group so that the faculty members could try their best to answer those. So we have come to the last question. I ask Neelanjana to ask the question. 1 minute.
Neelanjana, yes.
Sir, Namaskar, sir.
Namaskar, tell me.
So my question is that is it true that the Earth is going to end one day?
Yeah. So as I mentioned, there are. It's a very depressing thought. So the one is that once the sun becomes a red giant star, you can later on Google and read about what red giant is. 4,500 million years from now, the sun is going to become what is known as a red giant star. At that time, the sun is going to expand itself like an inflating balloon. It's going to expand itself and it's going to become larger than what it is right now. It's going to become very large. And at that point, life on Earth will definitely end. But that is 4,500 million years from now. So you do not have to worry, Neelanjana, right now. But a more imminent threat, as you probably know, is the human impact on our environment. I'm sure you must have read in the newspapers or you must have heard from your teachers or from your parents about climate change. The way we live our life, the way we organize our life, we are being completely insensitive to the environment that is around us. Carbon emissions from our automobiles, carbon emissions from our power generating plants, carbon emissions from all human activities, that is slowly warming up our planet. So our planet is average global temperature has shot up by approximately 1 degree centigrade in the last 100 years or so. And this is going to have a much bigger impact in the immediate future for life on Earth, especially life forms like us, who are very vulnerable to any kind of changes. Okay, so I think, therefore, it's very important that all of us take a very close look at what we can do in terms of our own individual selves. As individuals, what we can do to prevent this global climate catastrophe that is looming large over us. Okay, so the problem is global, but the solution has to be local. Okay, individually, each one of us have to contribute something towards it. Our zone of influence is ourselves, right? So unless we bring about a certain change in the way we go about with our daily life, problems like global warming, we will not be able to address. So that is the other imminent problem that is facing us. And the solution to that problem lies with all of us.
Thank you very much,
Yeah.
sir. I was actually impressed by the ways how children think to ask their questions.
Yeah, exactly.
I'm really thankful. I don't know. You must have a very much workload. In that time, you have come to answer our questions, and you are such a wonderful class. I'm really thankful. I thank on behalf of all the children, on behalf of Astro Club. Thank you, sir.
Thank you, Sriram. I think you moderated the questions very well. You went through all the questions and did an excellent job. And thank you, Jayanti Ganapati ji, for yet again inviting me. Yeah, thank you. Thanks for the opportunity. And what I will do is, I can see from the chat box that many of you have read a lot of astronomy, and there are questions about a lot of advanced topics in astrophysics that has come in the chat box. So I will share with Jayanti teacher a list of books that you can probably read to further your understanding and knowledge about astrophysics. These are popular science books. They are not hardcore textbooks. So I will WhatsApp her the names of those books, and she can probably share it with you. Okay. So keep learning, keep wondering. And the next time you look up into the night sky, when you see these twinkling stars in the sky, remember that each one of those stars have one or more planets revolving around.
That's a wonderful statement. Anyway, and definitely this will be motivating some of the children to join your IIST. Yes.
Yeah, sure. Yes, I look forward to seeing some of you. Yeah.
Yes. Really informative, and as though you are not well, still you are kind enough to speak to the children. Thank you, sir, so much. On behalf of, again, as Sriram told, behalf of Astro Club, I really thank you, sir, from bottom of my heart. And I appreciate all the children, those who have been here patiently listening to sir and asking questions. That means they are really interested. So really happy. And I thank Julius also. Because of him only we could manage all these things. Yes, thank you, sir. And Shanti
Thank
Mantra,
you.
Sriram. Thank you.
Yes, sir. Let's end with the Shanti Mantra.
Yes.
Om Asato ma Sadgamaya Tamaso ma Jyotirgamaya Mrityor ma Amritam Gamaya. Om Shanti Shanti Shanti. Om Lokah Samastah Sukhino Bhavantu. Lokah Samastah Sukhino Bhavantu. Lokah Samastah Sukhino Bhavantu. Om Shanti Shanti Shanti. Om Shri Gurubhyo Namaha. Harihi Om.